All right, going to try something a little bit different today because I want you to be able to see Desmos and also my calculator. So bear with me in case we have any terrible technological glitches, but we'll see how it goes. So today we're going to talk about compound interest, and the reason we're doing that is because really this is a geometric series or a sequence. Sequence really makes more sense. And that's exactly what we've been talking about. So we're going to take a look at this and see how we can create a formula or a geometric sequence or series out of kind of a financial situation, which is kind of fun. So we got Lisa here. She's got $10,000. She finds an investment, this is investment A, that guarantees 8% annually, and this is simple interest. So we've talked about simple interest before. Simple interest only is based on the original investment. It is not involved with like future amounts of money. So pretty easy to calculate. Let's see what goes on here. So first, they want them to know the amount of interest after 1 year. Well, the actual amount of interest, not the total investment, is just going to be 8% of 10,000. Which is, if we go to our calculator, 0.08 times 10,000 gives us $800. Probably could have done that in our heads, but here we are, right? So $800. So that means the total amount of the investment after 1 year is 10,000 plus 800, which is $10,800. Is it dollars? Yes. Okay, there we go. So to determine the total amount of the interest after 10 years, well, it's $800 each year. And some of you may know the I equals PRT formula, right? But basically all that is P times R gave us the 800, and now T is 10 years. So 800 times 10 is $8,000. So that's how much interest she has after 10 years. And the total amount of the investment will be 10,000 plus 8,000, which is $18,000 if I did my math right. Nice work, Lisa. 8% is incredible. If you find a bank that gives you 8%, never leave. All right, so simple interest is called simple because it's pretty simple to calculate, right? It's not too hard. Now, compound interest is a little bit different. When you have compound interest, what happens is the first year, we're still going to get the same amount of interest, right? The first year, we're still going to get $800 of interest. So at the end of year one, which is what question A asks, so it's still going to be 10,000. Usually we put the principal at the front, times, and they want to know how much interest will she receive on the amount of her investment during the first year. So 10,000 times 0.08, which is still 800. Go away. All right, so $800 still. And that means that the amount of the investment after 1 year is $10,000 plus what we just did here. And I'm going to write it that way for a specific reason. So we know it's 800, but I'm going to write it this way, $10,000 times 0.08. We can factor out the 10,000 for there. So it's 10,000 times 1 plus 0.08. So you've probably seen this formula before, but I wanted to show you where it comes from. Oftentimes, the IB will ask you to build a formula, and that's what I'm basically doing right here. So that is 10,000 times 1.08. 1.08. And if you've ever seen P times 1 plus R, or P times 1 plus RT or something like that, this is where that's coming from, right? So 10,000 times 1.08, which is 10,800. So it's the same as simple for the first year. But here's what goes crazy is what happens after 2 years. So after 2 years, that is C, not B. After 2 years, you get the 8% on the total amount after 1 year, right? So that's kind of weird. It's kind of weird the way I said that. But so now in a simple interest situation, right up here, the second year you get $800 again. The third year you get $800 again. This time, my interest that I'm going to get is the 10,800 multiplied by 0.08. So instead of only on the $10,000, I'm getting the interest on what was in the account at the end of 1 year. And this is how pretty much all bank accounts work. I've never heard of anyone that gets simple interest in a bank account. I'm actually going to write this a little bit differently. So where did that 10,800 come from? That came from, they just want the interest? No, they want the total amount of the investment. So I'm actually going to write that even differently. I'm going to write 10,800 plus 10,800 times 1.08. Not 1.08, 0.08, excuse me. right? Because this is the amount after 1 year. That's the total amount it's worth. And this is going to be the interest in year 2, right? The interest in year 2. So now I can factor again. I can pull out the 10,800, and I'm left with 1 plus 0.08. And now I'm going to ask, well, where did that 10,800 come from, right? The 10,800 came from 10,000. Whoops. I'm trying to build this formula here. Times 1.08. And now we're multiplying by 1.08 again. So what does that look like? That looks like 10,000 times 1.08 squared. And we're trying to build up to a formula here, which is why we're doing all of this extra work, right? So if you can kind of see what's happening here, after 3 years, it would be 10,000 times 1.808 cubed. And the reason is because you multiply by 1.08 to get the first year. Then you multiply by 1.08 to get the second year. Multiply by 1.08 to get the third year. You keep multiplying by 1.08, which is where the idea of this being a geometric sequence comes from, right? The first term is 10,000. And then if I want the nth term, right, un, it is going to be 10,000 times 1.08 to the, well, it's kind of weird here. The n minus 1, we've talked about this a little in the last video too, but so you might want to think about this as like u0, right? It's the initial amount. And then after 1 year, it will be times 1.08 to the 1. After 2 years, 1.08 to the 2. 3 years, 1.08 to the 3, right? And it's going to keep compounding that way. So let's actually get an answer here. So if I do 10,000, whoops, don't need a comma, times 1.08, whoops, raised to the second power, that'll work, gives me 11,664. Right, so $11,664 is how much they have after 2 years. Now, after n years, that's this formula right here. Right? And they want us to graph that on Desmos. Let's do that. So they want us to graph 10,000, no commas, times 1.08 raised to the, I'm going to use x here because we are dealing with x's and y's. You can do a y equals at the front there if you want to. And they want us to graph this on a certain window. Let's see, -5 to 45 for x. Let's go over here, change our window. -5 to 45, so we're looking at up to 45 years. And then they want us to do the y, -10,000 to 250,000, because it's going to be a lot of money. So -10,000 to 250,000. There we go. And we can see it curves upwards. Simple interest makes a line. Compound interest is exponential. It rises more quickly. So that 10-year value, let's see, for first our 2-year value, there's our 1-year value, exactly the same as the other one, 10,800. Our 2-year value, right there, 664. And now they say, hence, find the value after 10 years. So what I'm going to do here is I'm just going to look at what's going on at 10 years. So at 10 years, if I can get there we go, 21,589. So after 10 years, so this is D. So after 10 years, I don't know how to write that, but we're going to have 21,000, what did I say? 21,000, oh, come on, $589. Okay, and we could have done it with the formula, right? It should be 10,000 times 1.08 raised to the 10th. If we throw that into the calculator, sorry, I didn't let that come up, but 10,000 times 1.08 raised to the 10th should give us the same thing, right? Yeah, 21,589.25 cents. 3 sig figs, 21,600. There you go. So now, how does investment A compare to investment B? A is smaller than B, right? And why is one larger than the other? Because B is compounded, right? B is compounded. That means that we're getting the percentage on the total amount at the end of each year, which is way better than just getting the simple interest at the end of each year. Yep. All right. So now the reason I really wanted to have this calculator viewable is because I want to talk about the financial package in your calculator. It's really cool. And it does a lot of cool stuff, and we're going to see just a couple things right now. So using the financial package, use your GDC to confirm the value after 10 years. So in your calculator, we're going to go to apps, and number one should be finance. Some of you, it might be somewhere different, but something about finance, it should be in your apps, right? Applications right here. You got a lot of stuff here. I'm actually going to help you delete at some point because it's not allowed to have in the IB exam. You're only allowed to have finance and one other thing. I don't remember what it is. It's something about help. I don't know where it is. Doesn't matter. Anyway, so finance, let's jump in there. And you're going to choose TVM Solver, number one. All right, so again, I went to apps, finance, number one, and then TVM Solver, number one. And here we are. There's all kinds of letters here, and I'm going to explain what they all mean. So N is the number of periods that you're interested in. In this case, we have 10 years, right? We have 10 years going on, so I'm going to put 10 in for N. So it's the number of periods. It's not always the number of years. If something is happening like 4 times a year and you're doing 10 years, it'd be 40. We're going to see that in the next problem. I is the percent annual. We're going to say it's percent annually. So in this case, we're getting 8% annually. Notice it says times 100 here because you have to do it as a percentage. It is not 0.08. You put in 8 as in 8%. PV is the principal value. Now this is going to blow your minds a little bit. I'm going to put in negative 10,000. The reason it's negative is because we are paying that money to the bank, right? It is coming out of your pocket. Anytime you are losing money, you put it in as negative. And then the final value is going to be a positive because we're getting it back from the bank. So this PMT, sometimes you make payments to the bank at regular intervals. This we're just doing simple for now. So we're not paying any money to the bank like at the end of every year. So we're going to leave that at 0. But if we were, it would be negative as well. And hopefully our final value will be something positive we get back. PY and CY is payments per year and compounding per year. Both of those are going to stay at 1. I'm going to leave them exactly how they are. And we get the interest at the end of every year. So we're going to leave end there as well. So again, N, number of periods that are happening. In this case, 10 years. I, 8%. Principal value, we're putting $10,000 into the bank. We're giving $10,000 to the bank, so it's negative. No payments, we want to know the final value. That's why it hasn't calculated yet. So now what you're going to do is you're going to hit this. People always forget this. Alpha, enter. Alpha, enter. Notice right above enter it says green there, solve. That's going to give me that value. And look, it's exactly the same. $21,589.25-ish. So in this one, you might want to write that down. So our N was 10 for 10 years. Our I was 8%. Our PV was negative 10,000 because we paid that money to the bank. We didn't have any regular payments. If you make payments in, obviously your ending value is going to be higher. That's how people usually make payments because like you get paid every month. So maybe you put $100 in your bank account every month, something like that. Final value was what we wanted to find. I'm going to put a question mark there for now. Payments per year was 1, right? We're only getting that interest once per year. Compounding per year, also 1. Payment, PMT, they say you can always do it as the end, right? It says default is end, and it's pretty much true, right? There's a video example that shows a little bit more about the financial package. If you'd like to see that, we'll talk about it a lot more in class 2. And we calculated our final value, and that ended up being the same at $21,589. There we go. Yeah. All right. So once again, we have Lisa with $10,000 here. Another investment firm pays 8% annually, but it compounds quarterly. What that means is you get 8% per year, but they chop it into pieces. They chop it into 4 pieces. So you're getting 2% every quarter. And a quarter, it says right here, it's every 3 months, right? Because there are 12 months in a year. So every 3 months, you get 2% instead of getting 8% all year. The formulas for this get kind of crazy, but we're really just going to do this in our calculator, so it's not a big deal. So they say state the number of times the interest is added in the first year. 4 times, right? Because it's being paid quarterly, every quarter of a year, so 4 times over the course of the year. Show that the amount of money in the account after 1 year is $10,824.32. So, like I said, there is a formula for this. Basically, what you do is 10,000 times you do 1 plus, this time I'm going to do the percent divided in pieces, right? So I'm going to do 8%, 0.08 is going to be divided into 4 pieces. And then in the exponent, I'm going to do it to the 4th because it's happening 4 times over that course of the year. So instead of getting 8% once, you get 2% 4 times, right? So if you want to throw that into your calculator, you can. This formula I'm pretty sure is in your formula booklet, but I'm going to show you how to do it with the financial calculator too. So this is not a huge deal. So 10,000 times 1 plus, I'm going to do it exactly how it's written. If you don't know how to do this, alpha y equals, you can get the little fraction, right? N over d. So it gives you a nice little fraction there. 0.08 over 4, chop it into 4 pieces, close parentheses, raised to the power of 4. Hit enter. Should be 10,824.32. Look at that. 10,824.32. Perfect. Okay, now we're going to show how to do it with the financial calculator. Okay, so I'm going to go to Apps, Finance, TVM Solver. There are 4 total payment periods, right? 4 total payment periods because it's 1 year, but I'm being paid 4 times. So one way you can think about that is it's always going to be the n times the t, right? So n is going to be years multiplied by compounding periods, let's say. Right? So in this case, it's 1 year, but it's compounding 4 times. Okay? So we have 4 total. The I is 8%, right? That's the annual percentage, always. There are other ways to do this. I sometimes teach students how to do this differently, but I'm staying with the way that Mr. Rops likes to do this so that it doesn't get us in trouble down the road. Principal value is still $10,000. That's what we put in. There is no payment, but what I'm going to change here this time is we are compounding 4 times per year. We are compounding quarterly. That's the only thing I'm going to change. Now, final value, I'm going to hit alpha solve, and it's wrong. Uh-oh. What did I do? I did something wrong. Let's see. All right, I'm going to go back and do it the way that I usually do it. So I wonder if I do 1. I bet if I do 1, it's going to work. Let's see here. Alpha solve. Ah, yes. Okay, apologies. So n is, I need to go back and fix this because this is not correct. So n is just years. N is just the number of years. N is the number of years. And then, so if we do this in the kind of ROP style, so n is the number of years, the payments per year and compound per year is what we have to make sure we mess with, right? So 8% per year, but that happens over 4 periods. So then they know to divide it by 4, and that gives us the 10,824.32, which is perfect. That's what we were looking for. All right, so we got B, and we checked with the TVM, and it worked out just great. Perfect. So now, find an equation for the total amount of the investment after n years. So that's the equation that I just had right there, right? So it's going to be 10,000 times 1 plus 0.08 divided by 4 raised to the 4, do they want t? They want n, 4n, because that's the number of compounded payments we're going to have each year. So for D, make a general formula for your future value, FV, if the investment amount, present value or principal, is PV, the interest rate is I, the number of years is N, and the compound periods, CPY, is K. All right, well, that's going to be PV, that's our 10,000, times 1 plus our interest rate, but we have to divide that by 100, and also by our number of compound periods, which is K. So I over 100, that's just why we have a 0.08 here instead of an 8, right? That's, we just writing that, what's the word I want? The percentage we're writing as a decimal. And then raised to the NK, or KN, right? Because K is the number of times we're compounding, N is the number of years, and yeah, that's all there is to it. So PV, and that's equal to FV, our future value. PV times 1 plus I over 100K raised to the NK is our final value. And I'm pretty sure that's in your formula booklet. Now, they want us to do something with Desmos. Let's see. On Desmos, graph the total amount after n years of a 10,000 paying 8% per annum, but compounded all these different ways. All right? So, let's do that. So, we have... going to get rid of this. And I think this window will still be good. We'll see what happens. So 10,000. Oh, in fact, I shouldn't have done that. Can I get it back? Yes, perfect, because that's the annual one, right? So now we're going to do y equals 10,000 And the next one is semi-annually. Semi-annually, let's write this down here. Semi-annually means n is, so here n, k is 1, right? We're compounding once per year. Semi-annually is 2. Quarterly is 4. Monthly is 12, of course. For weekly, it's not exact, but we're going to use 52. 52 weeks in a year. And daily, 365. And we should have more money if we compound daily because you're compounding that amount more often, right? So you're always getting higher percent or the same percent, but on a higher value every time. So let's see what happens. So we have here 1 plus 0, let's write it like this. So 0.08 over, this one was semi-annually, so 2 raised to the 2x. 2x. There we go. And you see it's just a little bit better, right? It's a little bit better if you're compounding twice a year instead of just once per year. So I'm going to copy this, paste it here. So now we're dividing into, I believe it's quarterly, so 4 pieces, and it's raised to the 4x. And once again, see, you don't see a lot of difference until you get to like 40 years. Okay, and we might zoom in a little bit at the end to see what's going on there. So let's paste that here again. This time we are doing monthly, so 12, and that's raised to the 12x, just a little bit higher once again. Now we're going weekly, so it's 52 and 52x. And one more, daily, 365, and raised to the 365x. And you can see that changing from like, where are we here at 40 years? Changing from once a year to twice a year was a big change. And then it's not as much of a change going to daily. There's something called continuous compounding. Look at the difference between weeks and days. It's hardly anything. But I mean, after 40 years, you're talking about, let's see if we can compare all these. So let's do it. X equals 40, and then we can just see them exactly. So at 40 years, if you're compounding annually, that's way down here, I believe, the red. So if you're compounding annually, you have $217,000. If you're compounding twice a year, you've got an extra $13,000. That's pretty good. Going to quarterly, you're looking at another 7 over the semi-annual. If you're compounding, so that was 237. Compounding monthly, you have another, what, $5,000? Still pretty good. You're compounding weekly. That difference from 242 to 244 is only $2,000. And from weekly to daily, you're only looking at less than $1,000. So it's like $500 difference. Continuous compounding actually is based on the letter E. And if you're compounding as often as possible, like this will never be $1 million. There's a limit, kind of like we were talking about with the infinite geometric series, right? There's a limit on that, and eventually you're going to hit it for sure. All right, so E we did on Desmos, and we saw there was a big change from yearly to twice a year, but then smaller. Right? Going from like weekly to daily was not huge, even though it's 7 times as often. All right, and that was actually part F. F asked us to compare them. What are the similarities? What are the differences? All exponential, for sure. And it gets better the more times you compound, but the differences become smaller as you go bigger. Yeah. All right, still looking at investment B that guarantees 8% per year compounded yearly. Lisa starts to invest $10,000. If Lisa is 20 years old and wishes to retire at the age of 65, compare the interest accumulated in the first 25 years compared to the interest accumulated in the last 20 years. I see. Okay, so she's doing 45 years total. And we're looking at the interest in the first 25 years compared to the last 20 years. In terms of living your life, what is important to learn from this? These are important things, I suppose. All right, so let's look at the first 25 years. So we have 10,000 times 1.08 raised to the 25th. To the calculator, Batman. You could also do this on the graph, but let's just do 10,000. I don't know why I keep putting that comma in there. 10,000 times 1.08 raised to the 25th power gives us $68,484. So that is 64,000. What did I say? 484. And so interest, if we take away the $10,000, is 54,484. So if we look at how much she has, this is probably the best way to do it, at 65. So we do the whole 45 years, so 10,000 times 1.08 raised to the 45. That is going to be, let me just grab this, up arrow a couple times, change that to 45. She's going to have 319,204. $319,204. So the interest in, let's see, how do they want us to do this? They want us to compare the interest accumulated in the first 25 years to the interest accumulated in the last 20 years. So we just want to know the interest difference between those two. So if we subtract the 64, so minus the 64,484. So we can do that exactly in our calculator. We just go up and grab that, subtract it. We get $250,719 worth of interest just from between those two. So the interest here is $250,719, right? So look at that. In the last 20 years, the interest is about 5 times more. Right? It's fewer years, but it's a lot more interest. And what Mr. Ops is trying to drive to here, because he wrote this problem, is you should start investing early. Start investing early, because the key to investing is that you have a large principal, right? You have a large principal. And every year, if your principal is growing, you're going to have a bigger principal in your last 20 years than you do if you started later, right? So if you can start investing, if you have a job now, I mean, it's a good idea to start investing as early as possible. Put money in there every week, every month, whatever you can do. And that compound interest is going to be huge. It is mathematical, and it is so important to get that money in there and get it earning for you as soon as you can.